Okay, this lecture is about does leaky gut make you stupid? And it's with regard to the work of Douglas Kell and Etheresia Pretorius. This picture here kind of summarizes most of the key points of the talk. I'm going to go over some of the word slides, then I'll come back to these pictures. It's all going to make sense. And what it's going to basically come down to is, yes, leaky gut does potentially make you stupid and contribute to a lot of diseases besides the typical stuff known as autoimmune diseases. And the main cause of leaky gut, of course, is a lack of fiber from not eating enough plant food. And thus you don't feed the colon lining cells, the colonocytes, and therefore they can't maintain their tight junctions. So you get gaps in between the cells, and you'll absorb some LPS, lipopolysaccharide, the toxin from gram-negative bacteria, LTA, lipoteichoic acid from the gram-positive bacteria. Some bacteria themselves will get across the gut intestinal blood barrier, and you get these bacteria in your blood. The bacteria usually are dormant because the blood has almost no iron in it. So these bacteria cannot multiply, but they will persist as dormant bacteria in your blood for some time. So normally after you eat, the food material and this other leaky gut material goes up towards your liver through the superior mesenteric vein, SMV, to the portal vein and into the liver. When the liver senses there's inflammation, the liver releases these chemicals called acute phase reactants. Acute phase reactants include hepcidin, hep as in hepatic, made in the liver, cidin as in to kill, it kills bacteria. The way hepcidin kills bacteria is it's going to block ferroportin, the iron absorption door. We talked about that in a previous lecture. That's probably why I went through all those previous iron lectures. It was sort of a build-up in part to this lecture. This is going to be a more sophisticated lecture about the relationship between elevated iron levels and dementia, cognitive impairment, and generalized systemic inflammation, and being prothrombotic. Okay, Fibrinogen, one of these acute phase reactants, is a clotting protein, and it normally has a double helix shape. Well, I'm going to show you that one second. So these are my double helix, or my alpha helix is what I really want to call them. I'm going to show you the mechanism of how blood clots, how prions form in the brain, and I think that's good to know. You just have a sense of it, because you're going to hear about this stuff, and the words will become meaningful to you when you understand them. So LPS, lipopolysaccharide, predisposes to clotting. Excess free iron in the body, not bound to transferrin, or ferritin predisposes to thrombosis, and the configuration of the fibrinogen proteins will progressively transform from this alpha helix shape, like a coil, like the cylinder, to more of a flattened shape, like a beta pleated sheet. And we'll show how that all matters here in just a moment. Okay, so this work is coming largely from, it's basically a summary of the research of Douglas Kell, PhD. The guy's brilliant, okay? He's from England, he's brilliant, but here's what I think is funny. This guy's a brilliant researcher and he's fat, okay? So that's how it is in sort of the modern Western world of medicine. People can be experts on so-called health topics but still be fat. And so what he needs to do, if you're watching this, Doug, listen to my video, McDougall, Esselstein, Chef AJ, you'll lose the weight, you'll be healthy, okay? You'll appreciate it. All right, and by the way, my advice, never listen to advice from a fat person about nutrition. If they can't fix their own problem, they don't know enough, okay? Anybody who knows enough about nutrition, low-fat vegan, they'll fix their weight. Okay, his partner is a lady doctor from South Africa. Her name is Etheresia Pretorius. So her name's kind of easy to remember. It's kind of funny. Her first name, Ether, like the anesthetic. Name your daughter after anesthetic, okay? And then Pretorius is like the place. Okay. So anyways, research shows main spots bacteria get in the body, leaky gums in your mouth, leaky gut in your intestinal tract. I've got multiple previous lectures about leaky gut, so you can hear all about that and how to protect your teeth. Okay, mammals prevent bacterial growth by sequestering iron. So we talked about the big regulator of iron is hepcidin. It stops iron absorption because it blocks ferroportin. Ferroiron portin is a door. It blocks the ferroportin iron door on the duodenal cells. We'll see a picture of that in just a moment. When people become iron overloaded, as men routinely do after puberty and women after menopause, they're more at risk to have free iron in their blood. And that can cause all kinds of oxidative stress, and it also makes the blood more thrombotic. You get a lot of iron released into the blood if you have cells die in your body, especially liver cells, because liver cells store tons of iron. When they die, they'll release their ferritins. Their ferritins will let go of their iron, and it just goes around floating free in the blood, and that can cause reactivation of dormant bacteria. When a person is excessively chronically stressed out, the catecholamines can function as siderophores. Sidero is iron, 4 is to transport entry, so they facilitate the transfer of iron into bacteria. Bacteria can't grow without iron. Cancer can't grow without iron. So that's how, those are two major ways we prevent cancer growth and bacterial growth, is by sequestering iron, preventing iron from being available in our blood. Okay, when dormant bacteria come out of hibernation or dormancy, they will sometimes release LPS, lipopolysaccharide, also known as endotoxin from gram-negative bacteria, or lipoteichoic acid from gram-positive bacteria. We talked about LPS being inflammatory, causing the liver to release acute phase reactants like the fibrinogen. LPS is prothrombotic. It can distort the shape of fibrinogen, pushing it to be more likely to form a clot and to form a clot relatively resistant to being dissolved to thrombolysis. It's more distorted in its appearance. If there's abnormal blood-brain barrier permeability, the fibrinogen can cause precipitation of beta amyloid proteins in the brain and contribute to cognitive impairment through the beta amyloid mechanism. I actually think vascular causes of decreased brain perfusion, decreased brain glucose and whatnot are a more significant cause of dementia, but this contributes to it. And this is also the beginning. What I'm doing is I'm reviewing all the brain stuff, and I'm going through now the beta amyloid theory mechanisms of cognitive impairment. And so that's kind of what this lecture is about. And out of all of them, this is my favorite beta amyloid theories. There's a lot of stuff to know about beta amyloid, but again, if you fix everything in terms of the vascular causes of dementia, you're going to be 80% of the way towards fixing all this stuff. And then just add on this stuff. How do you prevent leaky gut and you avoid iron overload? And you're really going to be in fantastic position to have the lowest possible risk of dementia. Okay, so free iron is iron that is free, not bound to anything, not bound to transferrin, the blood carrier of iron, not bound to ferritin, the intracellular storage. And then, of course, we got iron bound to our hemoglobin and our cytochrome enzymes and in our electron transport chain complexes. Okay, when iron is free, it can be autocatalytic and it can redox cycle between Fe2 plus and Fe3 plus. Have a picture of that in just a moment. Free iron can generate ROS, reactive oxygen species, through the Fenton reaction. I remembered Fe for Fenton, that iron is a cofactor to catalyze conversion of H2O2 hydrogen peroxide into hydroxyl radicals. And the hydroxyl radicals just react with whatever's next to them and destroy it, okay? And that's why extra iron is also prothrombotic, meaning that it predisposes to clot formation. So it's bad in a lot of ways. Okay, real quick on dormant bacteria. This is something that most people are not familiar with. I've even talked to some infectious disease docs, and they didn't really understand this question very well, which was kind of surprising to me. Everybody knows that some bacteria obviously have a dormant phase, like tuberculosis. That can be reactivated years later when a person's immunocompromised. Syphilis, of course, it can be reactivated years later, and a person can die from syphilis. Syphilis used to be real common, you know. Winston Churchill's dad died from it. Al Capone died from it. Nietzsche died from it. And there's others, a lot of other famous people. Lyme disease, that's an interesting one. They thought Chris Christopherson had Alzheimer's, and it turned out he had Lyme disease, and his condition improved when he got better treatment for that. But anyways, these are all bacteria known to have dormant phases. It turns out there's a lot of less famous bacteria that also have dormant phases. Another thing too, like viruses. We all know you can have a dormant phase on a virus. Everybody knows you can get dormant phase of herpes virus, you know, in the genital area. You can get herpes virus, the other type of herpes virus, as a cold sore that can be reactivated. It almost seems as if the herpes virus has a gauge to measure your cortisol level, your stress hormone level in your blood. And when you're all stressed out, your immune system's compromised. Virus reactivates. Some bacteria, they can live inside your white blood cells or your red blood cells, like Bartonella from cat scratch disease. You know, people may not like me saying this, but man, I'm not a big fan of cats because I worry about getting scratched by a cat. They kind of make me nervous. Cats, harder to predict them, hard to control them. You know, I don't got the best social skills to begin with. Francisella tularensis, mycoplasma, there are other bacteria known for that. Dormant bacteria, that was proven, you know, decades ago with Micrococcus luteus. And by the way, I got references for all this stuff in the back of the in the back of this lecture at the end. They'll have a summary of the references. Plus, I can also tell you, if you study Escherichia pretorius and Douglas Kell online, they've got plenty of videos talking about all their data and the theory. They're both very intelligent. They're smart people. Okay. Let's see. Then you know, what's his name? Cal jokes about the bacteria in the blood being like Schrodinger's cat. Are they alive or are they dead? Because before, what is now known to be dormant was previously thought to be dead. And so that arose the question of Schrodinger's cat, the quantum physics joke about is the cat alive or dead based on, predictive properties of... Anyways, when donor blood is cultured anaerobically, they found that in addition to aerobic, if you only culture it aerobically, you only get 0.1% grow out something. However, when you culture it anaerobically under optimal conditions, 35% grow out some bacteria, especially Propionibacterium acnes. So that's also part of why people have increased risk of infections after they've received a blood transfusion. They're going to have more dormant bacteria. Plus, they're going to have a whole bunch of free iron floating around if some of the RBCs have lysed. Okay, free iron can cause dormant bacteria to be reactivated. That's an important point in this talk. And the reactivated bacteria can release LPS, the gram-negatives. That interacts with toll-like receptor number 4. The gram-positives can release LTA, lipoteichoic acid. And that's similar in its severity and toxicity as LPS. That can interact with toll-like receptor number 2. And we don't need to get into all that toll-like receptor stuff, but just so you heard of it. The combination of harmful effects from free iron and dormant bacteria is called the iron dysregulation and dormant microbe hypothesis by Douglas Kell and Etheresia Pretorius. So they became pretty famous for coming up with this theory in their lectures. And like I said, the video lecture by Kell on this subject is just brilliant. It's a brilliant lecture. It's really great. And she's got some really good lectures online as well. Okay, leaky gut is associated with lowered vitamin D according to Kell and Pretorius. So that might be a reason why some people are having lower vitamin D, contributing to it. Inflammation is prothrombotic, and I think that's a key point. That's why you want to minimize total body inflammation, because it just adds a little bit to you being prothrombotic. You don't want to be prothrombotic. The main reason people die is because they plug up an artery in their heart. They stroke because they plug up an artery in the brain. So you don't want stuff that makes you unnecessarily thrombotic. And the liver releases acute phase reactants, as we spoke about. In particular, fibrinogen was shown in the picture, the drawing, but also factor 8, antihemophilic factor, and von Willebrand factor. Okay, they're all clotting factors to make you more likely to clot. That's bad. Stress also increases these same factors, so it puts you at increased risk to clot. Okay. In addition, the LPS and the LTA, the toxins from the bacteria, they tend to make the clot more distorted, more they described as being amyloidogenic, more of a beaded pleated sheet aggregation type shape, and that's a little more resistant to lysis, to dissolving. Okay. So we do get bacteria in our bodies through leaky gut. Luckily, the ones that get in, they're usually asymptomatic and dormant until they start going through all this reactivation phase. So this happens more as people get older, because as they get older, they got a lot more free iron. So the good thing is just, prevent it as best you can, and you got a lot of ability to prevent this stuff. This is just a slide from a previous lecture on iron showing that when you eat iron, it's absorbed in the duodenum, proximal small bowel, and then it goes from these enterocytes, the lining cells of the duodenum, through the FP for ferroportin. Ferroportin, we just talked about it, is blocked by hepcidin, the liver-produced thing that kills bacteria, by blocking iron coming into the body, so the bacteria essentially starve to death or starve into dormancy. Normally, when things are good, transferrin, our little kayak-like boat, so to speak, will pick up iron from the ferroportin at duodenal absorption and carry it around the blood to wherever it needs to go. Bone marrow is like the factory to make cells. Spleens, like where red blood cells die at 120 days. The spleen is the RBC graveyard. Ferritins are the intracellular molecules. Each one individually stores about 4,500 iron molecules, whereas transferrin can only store about 2. It only stores 2 iron molecules at a time. NTBI, you'll see that abbreviation. That's non-transferrin bound iron in the blood. That's the free iron. That's the bad stuff. The liver is the metabolic workhorse of the body, and liver cells tend to store a lot of iron. Ferriportin is just ferro for iron, portin is door, so it's the iron door, letting iron into the body. It's the door that lets iron into the body. This is just a diagram we saw in the iron lectures, the fact that right after puberty, about 20 years of age, a man starts accumulating tons of iron if he eats a meat, processed food, westernized diet. A woman, because of her menstruation, really doesn't go up much in iron. Also because, she's delivering babies, she's going to bleed some at that time. And then until menopause, then she starts to accumulate iron quite rapidly. This is just a diagram showing redox cycling. So redox cycling is when the Fe3 plus keeps going back and forth, Fe3 plus, Fe2 plus, Fe3 plus, Fe2 plus, and in the process, it can throw off electrons to oxygen, and it can generate reactive oxygen species. In particular, the important one for our purposes is the Fenton reaction. So Fe for Fenton, Fe for iron, and that can convert hydrogen peroxide into hydroxyl radical. And then the hydroxyl radical reacts with whatever's around it and damages it. It can damage plasma membranes from the blood. If it's inside the mitochondria, it'll damage the mitochondrial membrane. But it's real toxic. So free iron is really bad. We've talked about it before. Like Weinberg is the guy I first heard this analogy from, that iron is like fire. You want in your house, you want fire in the stove, you want fire in the fireplace. Great. Cook your food, keep your house warm. But you don't want iron anywhere else. And it's the same thing in the human body. You want iron where it belongs. And as bound to hemoglobin for oxygen delivery, you want it in your cytochrome enzymes, you want it in your electron transport chain complexes, you want it anywhere it's doing a useful job. You don't want it free, because that's where it causes trouble. Okay, this is just showing how in the mitochondria, when hydrogen peroxide is not able to be neutralized rapidly enough by catalase, the Fenton reaction can occur, produce hydroxyl radical, and it can trash by lipid peroxidation in the intermitochondrial membrane. And the same thing can happen in the blood, trashing plasma membranes of cells. And there's markers for all this stuff. We'll list those in just a moment. Okay, so just a little bit more summary on what iron can do. Normally, the human body makes tremendous effort to minimize the presence of iron everywhere, to keep it from being free. Free iron is released anytime cells are dying, but especially with liver cells, because they have a lot of stored iron. And then the ferritin, once it's released from the dead cell, it also lets go of its iron. When a person has trauma, they can have tissue damage from the trauma, injury, blunt trauma to the tissue, and that can release iron from those damaged cells. You'll sometimes see that an old person has a fall, and they just progressively go down the tubes. They start getting infections and whatnot with all this free iron floating around. Free iron, like we talked about, can reactivate dormant bacteria. The bacteria need it to grow. Cancer needs it to grow. A cancer cell is very much like an anaerobic bacteria. It de-differentiates, running primarily on anaerobic metabolism and just out to help itself grow, rather than functioning as part of an organ, part of the liver, or part of some other tissue where it has a job to do that requires lots of energy. It goes into a low energy state, relatively speaking, in terms of it just wants to replicate. It doesn't care about helping the liver to do what the liver needs to do, for example. Free iron redox cycles between Fe2 plus, Fe3 plus. We talked about the Fenton reaction. Here's the biomarkers of oxidative stress, meaning that they can check these in the blood or the urine as indicators that a person is having high amounts of oxidative stress. Ferritin is normally located inside of cells, so it should not be in the blood. The fact it's in the blood at all is an indicator of cell death, and it's measured in real small quantities, in nanogram amounts. But ferritin levels are useful for predicting your risk of iron overload type side effects. The more iron a person has, the more distorted their red blood cells tend to be, because it can distort the shape of RBCs, and the more they're going to have in their urine markers of DNA damage, like 8-hydroxy-deoxyguanosine, for example. So this stuff's all been researched a lot. Here's how iron sequestration works. In an egg, for example, the yolk is where the baby chicken embryo is developing. The egg white around it is like this protein with a lack of iron. So the egg shell is permeable, but bacteria can never make it to the yolk because they can't survive passing through the iron-free egg white. They won't be able to replicate. And I said it's just like a human who tries to walk through the desert a long distance. They can't do it because there's no water. Just like a bacteria needs iron to replicate, we need water to survive. So this method of sequestering iron is very effective for preventing bacteria growth and cancer. Okay, here's a picture now, getting back to our summary. So once again, lack of dietary fiber plus other causes of leaky gut, like antibiotics, processed foods with the emulsifiers, which are like saturated fat from meat. They damage the plasma membranes of the lining cells, the enterocytes here. The colonocytes are also called in the colon. And because of that, you can't maintain tight junctions. You get leaky gut. Bacteria will get across into the blood. LPS, LTA will get across into the blood, travel up through this vein. I labeled it superior mesenteric vein. They go to the liver, and inside the liver, The liver senses the inflammation, releases the acute phase reactants like hepcidin to kill the bacteria by sequestering iron, fibrinogen to form blood clots. You want to form blood clots because throwing blood clots are like a net you can throw over bacteria to sort of trap them in one location. Then the immune cells can come and kill the bacteria, finish them off. Okay, so these are some of the things the human body does to control infections quickly. All right, and then here's showing this fibrinogen then gets into the blood. It starts out with this shape here, kind of like a slinky or a coil. And I was going to show you, here's how it works. I thought this was kind of interesting. So they're like a coil. See how this is cylindrical? And what happens is, it's hard to stack up all these things. You know, I got a couple of these. These are from paper towel rolls, all right? It's hard to really stack these things up. So what you have to do, what happens is though, when they're in the presence of lipopolysaccharide or free oxygen generating reactive oxygen species, they get flattened. So let me smush these things. I'm going to smush them flat. And these are standard protein shapes to go from being, this is called an alpha helix, like a coil. And then if it's smushed and flattened out, then it becomes a beta pleated sheet. And you see how it's very easy to stack these beta pleated sheets? And trust me, this is a big thing to know what I'm telling you. This is like a key concept in protein folding and cellular injury. So normally these proteins are supposed to be alpha helix. When they're all smushed together and flattened like beta pleated sheets, you can stack together tons of them. You can stack this thing up to the ceiling. The bigger a molecule is, the more likely it is to become solid, to precipitate. A protein can only be functional when it's in a liquid form, dissolved within the aqueous solution, the water-like solution of the body. When you get all these proteins aggregating into beta-pleated sheets, they become insoluble and they precipitate. They're no longer functional. They become this big bulky thing, and it can push on other things, and that mass effect of pushing on other things, that can cause other adjacent proteins. So it can be like, it can propagate. These proteins are beta-pleated sheet. They hit over here, they smash these proteins, and when they smash these proteins, they become beta-pleated sheet into an insoluble aggregate, and thus they can propagate. And this is the method. Not only does fibrinogen become clotted, and then especially a distorted clot in the presence of LPS and free iron, but the same thing happens to beta amyloid protein. We're going to talk about that and show a diagram of that in just a moment, but it goes from being water-soluble to an oligomer aggregate of a few to this big polymer aggregates of many as it moves into a beta-pleated sheet configuration, and that has mass effect on the plasma membrane receptors of the adjacent neurons. It has mass effect upon the adjacent beta amyloid protein associated with adjacent neurons, and thus it can damage them, make them fold abnormally, go into beta-pleated sheet stack configurations, and push that on and thus propagate. Because people wondered, how could a protein, a dead thing, these prions, propagate? And that's how they could do it. So this is a really important concept, going from alpha helix to beta pleated sheet. Okay, so a little bit more descriptive terminology on protein folding shapes and prions. So alpha helix is when it was round. We talked about, hopefully it would stay round. And when it's round, you're going to have hydrogen bonds holding this thing together. I showed the hydrogens on that diagram. Versus when you go into beta-pleated sheet, the hydrogen bonds will form, instead of being inside of it, they're going to form in between the two, like stick the two adjacent ones. Hard for me to like that, stick them together, okay? So that's bad. So they're intra within the same thing in the alpha helix, whereas they're inter between adjacent beta sheets, separate molecules. Okay, and then LPS causes fibrinogen to clot more intensely and to be distorted in its shape. And it increases the tendency of beta amyloid to do something similar, to form these big aggregates. So the beta sheets are more likely to bind to several other beta sheets, form oligomers. The oligomers get bigger and form these big polymer aggregates. So basically, beta pleated sheets, so alpha helix is like a cylindrical thing, whereas a beta pleated sheet's flat, like on my flat hand, and they can stack up one on top of another, like sheets of paper, tons of them. And you get these giant insoluble aggregates. And that's what your beta amyloid senile plaques are like in Alzheimer's dementia, in the extracellular space. To be active, a protein must be soluble. We talked about that. When it aggregates, it can have mass effect on adjacent neurons, and this is the possible mechanism for propagation of prions. A prion is a protein that is infective and can potentially propagate. So the typical nomenclature is going to be PRPC for a normal prion protein in its normal configuration, and it goes into a prion protein S as in scrapie form. Scrapie was a name for the sheep that had this encephalopathy due to a prion protein mechanism because they had so much itching, pruritus, they would scrape themselves on the ground and scrape their skin off, and so it was called scrapies. So that's where that comes from. You know, sometimes see it SC for scrapies. All right, so getting back to this, we talked about it. You got the fibrinogen. The fibrinogen comes here. Here's what I meant by these intramolecular hydrogen bonds. They're keeping the alpha helix and alpha helix configuration, all these hydrogen bonds. Versus when you go to beta-pleated sheets, the hydrogen bonds are now between separate molecules. Okay, separate molecules of beta-pleated sheet of fibrin. All right, so and then the LPS and the free iron were making the whole thing worse, more severe, more intense, with more distorted clot shapes. Okay, so what's the whole point of all this lecture? I went through all that complicated stuff just to give you a deeper understanding of it, but the whole point is avoid everything that causes leaky gut, and we've gone through all that. I got a whole lecture on a checklist of the stuff that causes leaky gut, but the main things, you know, the meat causes it with the saturated fat intercalating the plasma membrane of the enterocytes, oils being very toxic to enterocyte lining, processed food because emulsifiers kind of similar to sat fat intercalating through those membranes, antibiotics disrupting the gut flora, the bacteria there, excessive stress perhaps by causing ischemia due to splanchnic vasoconstriction, decreasing the blood supply to the gut lining. Perhaps that's the reason why they also increase leaky gut, excessive stress, which means caffeine is going to contribute to that. Cl minus, F minus from the water can do it. And there's a bunch of other things. I have a whole list in that other lecture. Take good care of your teeth because leaky gums can also let bacteria get into your blood. Avoid liver toxins like alcohol. When they kill liver cells, those liver cells will release a lot of iron into the blood. I recommend only eat organic because some of the herbicides associated with non-organic food like GP, they predispose to fatty liver. Fatty liver over time becomes inflammatory and leads to killing of liver cells, more release of iron into the blood. High-fat diet in general is a real bad idea. It predisposes you to fatty liver, to diabetes, etc. To avoid iron, excess iron in your diet, of course you avoid meat, but watch out for iron-fortified grains. When I was younger, I used to eat one of these Raisin Bran cereals. So one of them had a lot of iron fortification, 25% of your daily requirement in one serving. So I used to eat the whole box real fast. Stupid, I didn't know any better. Iron fortified multivitamins, stay away from all that stuff. You want to lower your iron levels almost everyone. I mean, you can check your iron levels, find out where you're at. And, if you're a menstruating woman, you might even be low, but for everyone else, they're almost always, not almost always, but very often on the high side. Consider donating blood, check with your doctor for that. So anyways, that was the whole point of this. By avoiding the risk factors of leaky gut and avoiding the risk factors of iron overload, you further optimize your health and reduce these risks of progressing towards contributing to cognitive impairment. There's some people who think this is the main thing that causes dementia. I don't think so. I think it's a contributing cause, not the main cause. Okay, then I had the references here. So these are some of the papers by the different researchers who've done a lot of work with iron. And, most of the material in this talk especially comes from the work of Douglas, Kell, and Pretorius. They've got a lot of research papers they've published on these subjects. They've also got really good online lectures, and this one is a really good one. So if you're interested in learning more about this, check out the work, especially of Douglas, Kell, and Theresia Pretorius. They're both really good, and you'll learn a lot from them. So that's it.